There you go. Doing that homework that was due like 10 weeks ago.
I still have many people who have to turn in their homework. Well, actually, I think I have a majority in now, but still some outstanding. There's still 2 assignments to go. Okay, so now we have a QR factorization. How does that really help us? Okay, so given this QR factorization, and once you have the full one, then of course the thin one, you get that for free. Here's what you do. So you have b minus ax 2 norm, and you can multiply this vector by any orthogonal matrix that preserves the 2 norm. So what we'll do is multiply that by Q transpose. But what I can do there is, so Q transpose B, this is going to be an M vector. So I'm going to break that down into blocks, call them C and D. So this has the first n components, and the other n minus n are sitting in D. Now, since A is equal to Q times R, I can multiply both sides of that by Q transpose. So Q transpose A is equal to R. So now what I have is Rx, but R breaks down into R1, it's an n by n matrix, and then zeros. So you have n minus n rows of zeros here. So I'll just fill in x here. Actually, that's not, actually, yes, now it is a 0 vector. Okay. But now what I can do, since this is a vector norm, I can consider the sums of squares of these blocks separately. So, actually, to make it easier, I'm going to square all of these. Okay. So, now what I have is just a sum of squares. There's no pesky square root to get in the way. So now I can write this as the 2 norm of C minus R1x plus the 2 norm squared of these lower components, but that is only going to give me D. So so when you're breaking apart components like that, when you're dealing with a 2 norm squared, this is a nice relationship to use. Because it lets you focus on these components, these portions of the vector separately. Now, D, that's something that's fixed, because D only depends on the QR factorization and also B. So there's nothing I can do to minimize this. Here, however, this involves my unknown, x. So what I can do is, I can make this a 0 vector. So I can solve R1 times x is equal to C. So as a result, the norm of B minus AX, if I want to make it as small as possible, it just turns out to be the 2 norm of D squared. Okay. Now, solving this system, R1 times x is equal to C, how do I do that in this case? What method can I use? What?
It's a upper triangular.
Yeah, upper triangular.
So yeah, back substitution.
Yeah, it's back substitution. So now the thing is, that part is easy. That takes order n squared operations. except the only reason you're able to do that is because you've gone to the trouble of computing a QR factorization, and that takes on the order of n cubed operation. So you're still doing a whole lot of work. Actually, I have to be careful here because this is, A is an m by n matrix, so this takes, let's see, mn squared floating point operations. All right, so we have this approach to solving least squares problem. So the actual steps are A is equal to Q1R1. So really the economy size or thin QR factorization is all that you really need. And then you go ahead and solve this, well, R1 times X is equal to C, but C you can get, that's Q1 transpose B, because you're taking that upper portion of Q transpose B. So if you have the thin QR factorization, this is enough to get the solution to the least squares problem. So QR factorization, that's a really expensive part. It's kind of like a Gaussian elimination. And then you do actual back substitution here, and you have a solution. Okay. So that's one approach, and the one of greatest interest to us for solving the full rank least squares problem. And I say full rank because what about the case where A does not have linearly independent columns? So that's called the rank deficient least squares problem. I won't be covering that because of time, but that's discussed like later on in chapter 6, like after section 6.3. So in that case, QR requires a form of pivoting. Instead of interchanging rows, you're actually interchanging columns. So there are a lot of parallels that can be made with QR factorization and Gaussian elimination. Okay. Any questions on the QR factorization approach to solving least squares? So we need this for iterative methods because you'll see some iterative methods like GMRes and MinRes that have a case of solving a least squares problem. A matrix is m plus 1 by m for some m. So you wouldn't use ordinary Gaussian elimination. We treat it as a least squares problem. Okay, so I'll touch briefly on the second approach of how to minimize the norm of B minus AX. So if I again look at the 2 norm of B minus AX squared, but I multiply it out. So the 2 norm of a vector squared, how can I write that as a dot product? What is it a dot product of? Well, what is transpose dot?
Itself, like
Yeah,
itself?
yes, dot product of itself. AX transpose B plus AX. So now I go ahead and multiply all that out, and I get B transpose B minus B transpose AX minus X transpose A transpose B plus X transpose A transpose AX. Now it turns out because of properties of a transpose, these 2 expressions are actually the same, assuming everything here is a real vector. So I can combine like terms. 2 X transpose A transpose B plus X transpose A transpose AX. Alright, so this is what I want to minimize. So what I can do is a function of X, all the n components of X. So I take the gradient of this. And what I get, well, this doesn't involve X at all, so its gradient will be 0. Here I'll have, this is a linear function of X, so it's kind of like a constant times X. So all I keep is a constant. So minus 2A transpose B. And this is a quadratic function of X. So it's like how you have a derivative of AX squared is 2AX. So I get 2A transpose AX. And I want this to equal the 0 vector. So what I do is solve what are called the normal equations. A transpose A X is equal to A transpose B. Now, AX equals B does not necessarily have a solution at all. This system does, if A has linearly independent columns. So what happens here, this is n by n, and since A has a full set of linearly independent columns, what kind of matrix is A transpose A? What can we call that? Anyone?
What was the question?
What type of matrix is A transpose A? What can we say about it? What properties might it have?
Well, it's symmetric.
It is symmetric.
And you said that its columns are.
Very linearly independent. Yeah, so that's important.
Does that mean it's invertible?
Well,
It is invertible, but there's something more we can say.
well, the fact that they're linearly independent, does that have anything to do with the columns being orthogonal?
Oh,
What does that?
that's just some pure factorization. But Q is orthogonal. Q1 is orthogonal columns, but A doesn't necessarily.
Okay.
It is symmetric. It's invertible. We can make a slightly stronger statement. So, instead of simply saying what it is,
It's symmetrical.
yes, it's symmetric.
Well, that's
I was going to say that a second ago, but I'm like, no, just that's going to be wrong.
Well, that's what I
Well,
was thinking. That's why I asked about the orthogonal.
I'll show you why it is. Because if I look at
Because that was like one of those little properties, I think, written
if I
down.
look at the 2 norm of A times X for any non-zero vector X, so that would be dot product of AX with itself. So that's X transpose A transpose AX. Now, if X is non-zero, AX is also going to be non-zero because of the linearly independent columns. So, remember, this has to be positive. So that's what I see as symmetric positive. So it's n by n and symmetric, positive, definite. So if you want, you could solve this using